Welcome back. Am I audible?
Yes, sir. You are audible, sir. You are audible.
Yeah. Okay. Thank you. So we will start our next session. So as I mentioned before the start of previous session, the next today's session and tomorrow's first session, we are going to have experts talking on RISC-V architectures. The first session we had Libin who had talked about Vega processor. So now the next two sessions we have experts who have worked with the Shakti platform. So I'm very happy to introduce our speaker for our next session, the co-coordinator of the FDP also, Dr. Tripti S. Warrier. Um, so Dr. Tripti Warrier is an assistant professor at the Department of Electronics, Cochin University and Science and Technology. She received her BTech degree from Government Model Engineering College, Trikakara. She received her PhD from the Department of Computer Science, Indian Institute of Technology, Madras. Her tenure as senior project engineer at Wipro Technologies gave her exposure in the area of front-end ASIC design, verification, and FPGA design. Her research interests include RISC-V processor design, domain-specific SoC design, hardware for edge, memory systems, and non-volatile memories. She has supervised multiple projects and published multiple papers in international journals and conferences in these domains. Currently, she is collaborating with an industry partner for the MAITI-funded project on embedded RISC-V processors for DSP and AI workload under the Chip to Startup program. So once again, I welcome Dr. Tripti to the session and handing over to you.
Yeah, thank you, Nalish. Very good evening to all of you, and I'm happy to be speaking in this FTP, and hope that interaction with me will help you to maybe work in this area. So I'll share my slides. Hope you are able to see my slides.
Yes, yes.
Yeah, thank you. So the topic for today is about, so maybe I will switch off my video so that it will be easier. Data. Okay, so the topic of my session is RISC-V ISA extensions for security application. So the previous sessions, previous session, we were very fortunate to be interacting with one of the designers of indigenous processor and happy to hear that so many activities are going on. I hope you should be proud to know that so many activities on RISC processor design is happening around. So the idea that he talked about was the basic processor design, and here I am trying to build to talk about a particular domain, how we can use RISC-V ISA and design a processor or an SoC for that particular domain. So the domain that I am talking about is security, security, and so we will be talking about a few of the activities that are happening, how we can do such design using existing basic RISC-V processor. So outline of the talk is just an introduction to RISC-V with respect to SoC design. Some of the points have been covered by Levin, but I will talk about something that with respect to what I am is relevant to my talk. And then we will talk about security applications specifically. And when we talk about security, we are talking about cryptographic applications. So how we can include features of that will improve the performance of a RISC-V system for cryptographic applications. So discussion based on cryptographic extensions, then custom extensions, bit manipulation will be discussed, and my take on how you can design and what kind of extension to use when we are designing systems. That's the summary. So RISC-V, why RISC-V? I think by this time you all will be clear on the fact that RISC-V is an open source ISA for which no royalty has to be paid, and we, as a researcher, can use it without any financial burden. So that's the advantage of having RISC-V. Other than that, most of the ISA is such that you can add. It's modular in nature. You can continue to add instructions and customize the processor for a specific application. So generally, there will be a base ISA, and then fixed standard extensions are also defined. We will see in the next couple of slides, but. So the thing is that you will be able to use RISC-V ISA and handle design a processor to handle a simple embedded processor to a high performance server. That is possible. That is the advantage of having using RISC-V ISA. So this is giving you a simple comparison between popular ISAs, x86 and ARM. So there are many chips using all these ISAs, but the architecture ISA is available for ARM and RISC-V, but for ARM you have to license it, whereas RISC-V it is free. So commercial IPs are not available for x86. You can only have buy products that which follow x86 directly. But in ARM case, you can have processor, you can have soft IPs that you can use for SoC design. And only there is one vendor for the IP, whereas RISC-V IPs, any company that customizes an IP for a particular a code design for a particular application can sell as an IP. So you will have large number of vendors in market who sell commercial IPs. So another very important advantage of RISC-V ISA is that because it is a base plus extension kind of an architecture, RISC-V you can add your own instructions and to tailor to customize the code for a particular application. So that is possible in RISC-V, which is not so easy in x86 or ARM. So it doesn't happen. Mostly doesn't happen in ARM and x86. You don't have the design, so you can't do anything about it. So you see how RISC-V architectures are flexible. I mean, ISA is flexible, and you can change, include new instructions based on your requirement. Then, like open source IP, both x86 and ARM are open source. Do not provide open source core IPs, whereas here they are available. So this is the notion behind RISC-V ISA being popular nowadays. So next slide is showing again comparing with other open source ISAs that are available. Spark V8, OpenRISC, and RISC-V are the ISAs, very popular ISAs. So base plus extension, the concept of base plus extension, base in ISA plus extension is available in RISC, whereas for Spark and OpenRISC, their ISAs are fixed. So you have a design with all the entire instruction set, or you don't have a design at all. That's how it will be. Then compact code. So similar to ARM ISA, where you have a 32-bit and a 16-bit ISA and compressed instructions, which will allow you to have high code density in your for embedded applications. RISC-V has a subset of instructions which use 16-bit representation. So you can have high code density there. Then quad floating point operations are available in RISC-V. Other than 32-bit address, 64 and 128-bit addresses are supported in RISC-V. Then all these open source softwares are ISAs are supported by software such as DCC, LLM, and then Linux for these ISAs are available. So So in terms of software, all of them look similar, but hardware features are different. So clearly we see that there are many advantages if you use RISC-V. So this slide is showing us the different instruction sets. I know we have already talked about few of them, but the concept is that base or integer is the basic instruction set that is part of any RISC-V processor design, and that in itself is able to run most of the applications. But now, why do you require an optional standard extension is based on the application that you are targeting. So if you see on the right hand side, there are a number of different extensions which are optional. You can and standard, which has been defined by the RISC-V community, which includes multiplication, compact instruction set. So if you are trying to look at embedded, maybe you will, and a high code density requirement, you may use base plus this compact instruction set, kind of of an ISA, and then design a hardware for it. Then we have single precision and double precision extensions, then atomic memory extensions, then bit manipulation, vector extensions, DSP, packed SIMD extensions, etc. are examples. So based on, so some of them are standards and some of them are non-standard. So at this point, I would say that if you look at this instruction extension subgroups, we will see them at different stages of development. So draft and develop will be a kind of sub extension which people are working on and has the feasibility of changing based on requirement. Then there is something called stable, where the set of instructions in that subgroup is almost stable but may change. Whereas when you say frozen, it's highly likely that it remains the same without any addition or subtraction. And finally, when you say ratified, it means that the group, RISC-V group, has accepted and there will be no further change in that instruction set. So some of these instruction sets have been ratified and will not change. Some of them may change. Different versions of it will come based on whether it is frozen or stable versions. So that is how it is. So looking at all these instruction subsets, how to choose what is a question that you may have in mind. So using bit manipulation, vector, and packed SIMD. SIMD is single instruction, multiple data kind of scenarios, which is generally used for DSP and DSP applications. So here I'm trying to explain application and how to choose extensions. So in this particular case, for bit manipulation, is basically used for security applications, encryption, decryption, keyring maintenance kind of thing. So most of the instructions in this subset will be implementing certain functions which are very frequently required for this application. Similarly, when you look at audio-video processing routers and communication kind of activity, we will see that packed SIMD set of subsets have instructions which will which will directly map to basic functions of these applications. So you may choose packed SIMD. Now, if you are looking at graphics and graphic processing, computer vision applications, we know that large number of data is available and same action is going to happen again and again. So their vector could be of use. So edge analytics and edge computing or intelligence in edge is somewhere in between, where all these subsets may be useful. So why are these subsets useful? As I said, they are useful because they have instructions which directly maps to very simple basic functions in the application. So you don't have to have a set of large number of instructions to do the task. Rather, a single instruction will replace that, and you have the hardware supporting it, so that the task becomes faster. So that's how these extensions speed up the processor and processing. And we see that based on application and the frequently used tasks in the applications, that will directly map to certain specific instruction set. That's how it is. So for a beginner, we can think something like this, where so if you are not bothered about your we all know that if we are not bothered about our power or area, we can have all these extensions. So what is stopping you from having all these extensions as part of the design is that the area increases, and when the area is large, and automatically the power is larger, and probably when you have large number of complex tasks happening, your clock frequency may be reduced, so delay may be a problem. So generally, if for basically you can do something like this. That is, you have a benchmark. Benchmark is, I'm talking about an application for a specific domain, and if I am targeting a processor design for that specific domain, a simple thing that we can do to know which extension to use is to compile that application and generate a assembly program, and then profile it, and then identify which instructions are. So you will have an number of counts for each set of instruction, and looking at it, you can decide which instructions to be available in your processing core, and accordingly, if you can map it to a particular extension, and then come up with a customized RISC-V for a particular application. So how do you know whether this hardware is good for that application? Is that after you design it, you have to do a performance estimation, and you will be able to run this program on this hardware and come up with performance numbers in terms of probably cycles, which will give you a delay and frequency and energy. So you may come, based on the profile data, you may have different possibilities which you can design and come up with this. And then when you actually implement, you can choose the best design that is possible. So implementation will be generally area versus speed trade-off. And this is a general procedure with which generally industry uses to come up with its own design. So this is, I'm just presenting of how you can start on this. So what is the advantage of RISC-V? As I said, it is available. ISA is available for use. In fact, a number of open source cores are available. Many universities across the world have come up with their own RISC-V implementations based on the ISA that I have discussed in the previous slides. And then it is available in GitHub, and you will be able to clone it and run programs in it and simulate and see. So secondly, it is modular in nature. ISA itself is modular in nature, which you will have a basic in integer, which can be extended based on your application requirement. So, and you have the freedom to choose which instruction to use, which instruction not to use. As and when the instructions, sub extensions get ratified, that is, once they fix the instruction subset, the compilers have been modified to support that. So and then you will be able to reuse a design done by anybody, which is available in open source to any other for your own use also. So these are the advantages. So you can use and change to create your own processor and exactly as per your requirement. That's the advantage of having a RISC-V use of having RISC-V ISA. So this is the journey of ISA. It is taken from literature from China. So probably they have shown some of the chips which have been developed there. But the story behind this, it started in 2010. India's progress we have seen in the during the last session. So here, what is the world doing is what I'm trying to project. It's the project of RISC-V started in 2010. So Berkeley came up with a 64-bit RISC-V vector processor. So we have Berkeley's rocket, and which is in 45 nanometer. Then there is out of order. So this is vector. You have out of order 64-bit, 64-bit out of order, and then we have 49 core out of order, 49 core system with which is server class kind of, where with out of order 32-bit processors. Then TSMC 12 nanometer out of order 64-bit cores are available. So what I'm trying to tell here is that some GPUs are available, and then for edge Q, that is for 5G SoC is available now using RISC-V. So you have 16-stage complex bigger systems with 64 512 cores. So what I'm trying to say is that corresponding to the traditional progress of devices using traditional ISAs, RISC-V is also people working in this community are also making sure that all kinds of processing cores are available based on RISC-V. So that's what I would want to, even though it started in 2010, there is a lot of work happening, and commercially chips are available. So that's the summary of this this slide. So going into the software part of it, so this is again showing similar the growth. So along with the software, we are having the hardware also. Along with the hardware, we are having the software also in development in software is also happening, and we are now after 2020, we are in a stage where we have RISC-V hardware with OS and RISC-V hardware for servers also. So what is the summary of these two slides is that you can use a RISC-V ISA and tailor make it to any of the any applications such as embedded and edge control. As a you can convert it in, you can design an embedded or edge controller, or you can have domain specific, where domain could be as complex as computer vision or communication, or you can have a high performance processor which go to servers where large amount supercomputers where large amount of computation has to happen, stringent timing has to be maintained. So all these things are possible. And we are looking at a particular domain in this session, which is security. So how can you accelerate a particular domain? How can you accelerate a particular domain is shown, a small summary is shown here. You have 3 techniques to do that. One is use a tightly coupled so we all are aware of the term acceleration. So accelerator is something that will speed up a particular task. And so since it's a domain, accelerators are the ones that we are all aware of. So one particular methodology is to include the accelerator into the RISC-V pipeline itself. So that is fetch, decode, execute, and in execute stage, along with ALU, you can have execution units which are helping you to, which is specific to your domain. So that is tightly coupled accelerator. Now, another implementation is that you may have a hardware which is doing a particular task, but you have not integrated it in the pipeline. Rather, you have it as a co-processor. And when it is a co-processor, at the decode stage, your decode stage, the instruction for co-processor will be different from instruction for something which is there in your execution unit. So decoder will identify that and then direct those set of instructions to the co-processor, and the response from this will be updated in the register file itself, and there will be an interface that allows you to do that. So clearly it is not as tightly coupled as this, but it's still, because decode stage is involved in doing that, you call the hardware through the decode stage, it is closer to the processor. Now, when I explain accelerator, you will understand why it is called a loosely coupled. So Here, accelerator has the hardware to do a particular task, but it is connected to the core through a common bus. So, in the previous session, if you would have come across the high performance bus, AXI buses that Libin was talking about, which is an interface for an external peripheral. So, this accelerator is like a peripheral, or not actually, it's like a memory. It will be considered as a memory. Memory will be connected through AXI bus, high performance bus. So accelerator will be connected to that high performance bus. And then using, when you write C programs, you will map your tasks to this accelerator using memory map. So communication of the core and the accelerator happens to the common data bus that is there. So instructions will be given through the bus, and accelerator will work on it and then broadcast it in the bus, and the data and that will be updated in the memory. So that's how it happens. So these are the different strategies in which acceleration can happen. And in this particular session, we will be talking about tightly coupled acceleration and maybe an example of coprocessor. Loosely coupled processor example are similar to implementations will be similar to what is there for any other application. That is AI ML applications or DSP applications. These kind of accelerators will be similar to that. So this is just an introduction so that you follow how to work for a domain and how to speed up, come up with hardware to speed up that particular domain. So as I said, this is a representative of having tightly coupled acceleration. And how do you do with extensions here is this extension that I talked about in the previous slide, maybe vector extension or bit manipulation extension. All of them are a set of instructions. So we have to come up with a unit which will be implementing those instructions and integrate it with my execution stage. So you have a modified instruction set from the original instruction set. So this extension could be a defined extension, that is properly defined standard or non-standard extension, or any non-standard, that is there is provision in ISA encoding for your own custom instruction. So you may add a custom instruction and include its execution in the execution stage. So when you do something like this, when you add an instruction, new instruction here, you will have to update software stack. That means you may have either you have to when you want to run a program which uses this extension, you have to compile. You have to have a compiler which identifies a sequence of C program snippet which can be mapped to that extension. That is, a compiler update may happen, or because you are the hardware designer and you have you know the hardware and you have good knowledge of the application. You can write the application in such a way that these instructions are inserted. That is, you know that using certain features of writing C code in C code, you can embed assembly. You can force a call of an assembly instruction. So using volatile. So in that case, the person who is developing the application has the knowledge of the hardware and has the knowledge of the domain, and he is purposefully replacing C code snippets with instructions which are extension instructions which will speed up the process. So that's how, if compiler doesn't support, this has to be done. So in whatever be the case, you have to update the software stack to support this. So if you are using extensions which have been ratified and approved by the RISC-V community, then most of the cases your LLVM or C++ compiler has the support for this, and it identifies the code snippets which is using extension when you compile, you give a compile option that these are the subsets that are available to you, instruction subsets available to you, and automatically that will be taken care. So only for maybe custom instruction, something like that has to be done from your side. So this diagram is showing what happens when it is an accelerator or coprocessor. When it is a coprocessor, your decode will take care of it. Decode will send a request to the coprocessor, and the response will be updated in memory or register suitably. If it is an accelerator, it would be through a common data bus. So when it is loosely coupled, things that you have to take care is that you have to have a hardware that accelerates. Other than that, you have to take care that you have how to communicate. That is AXI bus, that interface you can decide. Now you have to decide, and then also decide in your accelerator memory mapping. That is, accelerator will be addressed by what memory, and if there are configuration that you have to do, those all will be like, you will consider it as a how you are operating a peripheral, and you will have configuration registers, and then start and end all these the sequence of control that is required for completion of the task. That handshake has to happen. So generally that happens using memory maps, and that has to be taken. And sometimes you may have to use a software stack, or you have to intelligently maybe write a C program to ensure that this use the memory map and write the C program. May not have to update the software stack. So that's how it happens. So now we have an idea about what is happening. So I will be showing you some designs which are using some of these strategies. So for security, when you talk about security, we generally talk about cryptography. And so we are going to look at examples of how you can develop a tightly coupled RISC-V and loosely coupled. Different examples are there, but we are basically looking at three different strategies. And one is using cryptographic extensions directly, which is available, which some of it has been ratified, and it is part of the instruction set ISA now, extension instruction set. Then use of simpler instructions extensions to implement complex cryptographic algorithms, that is bit manipulation extension. And then custom extensions, which is writing your own instructions to do the task. So these are the designs we are going to discuss during the next few slides. So looking at cryptographic extensions for security, so for RISC-V, so there are two sets of extensions, scalar and vector. Scalar cryptography extensions are generally used for simpler cores that is embedded embedded in IoT applications or large application core, but not high performance systems. So these extensions support both 32-bit and 64-bit. So there are 9 sub extensions and 49 instructions in total, and each subsection has specific task. And if you see it, this has been ratified in November 2021, and why it is scalar is because it is using a register implementation, which is used by base instruction set itself. So to support this, except the execution unit, no change has to be and decoder, no change has to be done in the entire RISC-V design, already existing design. So when you look at these sub extensions, there are certain instructions in bit manipulation instruction extensions which support cryptography. So those are mentioned. The first two cases are examples, are subset of instructions from the bit manipulation which speeds up cryptography. That is careless multiplication and basic XOR and that kind of basic bit manipulation B type instruction set. Other than that, you have crossbar permutation subset, and then you have specific instructions for AES decryption and key scheduling, encryption and key scheduling for AES. This is another subset. So encryption, decryption, then SHA hash function, acceleration of SHA hash functions are there. Then these set of instructions are called NIST algorithm suite. So these are based, these subsets are required for NIST algorithms applications, whereas SM4 and SM3 hash functions are examples which are for other cryptographic suits. And when you say a standard cryptographic suit, all these extensions will be present. So any combination of this could be present in your RISC-V design. If you see the ZNK that I'm showing here, it has a subset of this. ZNK, as all these things have been defined. This is a NIST suit. So this is another subset. So you can choose. So when you say standard set, it is called ZK. Each each instruction extension in RISC-V has been given name. So ZK is the whole instruction suite of cryptographic, scalar cryptography. So this is scalar. So this is for cores which are simpler in nature and the register files are simpler in nature. Now, if you look at vector extension, this is a heavy extension in the sense it consists of 7 subsets with only 22 instructions, but to realize this logic, include this logic in any RISC-V code, the RISC-V code should have a vector support because it assumes that their operands are there in vector register. So generally, it is used for large application and server class cores. And that means, so the difference between them, if you look at the instruction subsets, they are still talking about AES and careless multiplication and SHA, etc. What it means is that here in this particular case, the instructions work on a vector, multiple elements which are stored in vector registers. So vector architecture allows you to, ISA allows you to define how many elements are, what size element, etc. is possible. So if you look at it, all these instructions are performing operations on large number of data simultaneously. So single instruction will work on multiple data parallelly because it has vector support. So these are generally, that's the difference between scalar and vector extension. So in the next slide, so these are subsets and definitions are there that is available in any standard literature. What I want to show here, this is from an implementation of scalar cryptographic extension. So this is snippet of code which is in RV32I. Now, by this time you are aware of what RV32I is. So it is 32-bit RISC-V core with integer support, and these are 2 different subsets of instructions. The first subset of instruction is implementing SHA 512. So this entire 9 set of instruction can be replaced by a single instruction, which is part of the scalar cryptographic extension. So this is the difference. So when you look at the, if you have a program where this action is happening, it will be replaced by 1 instruction. Similarly, here 10 instruction, 10 to 20, that is 11 instruction is replaced by the next SHA. So you see that code size has drastically reduced. So when there is a reduction in code size, and this instruction will be executed inside in the normal pipeline itself. If the clock frequency doesn't change by including this instruction, then you see that when the instruction count reduces, performance improves. Number of clock cycles to execute the same program reduces, and when clock cycle reduces, automatically performance improvement happens. On the right hand side, it's the result from the paper which shows, so all applications which are listed here are cryptographic applications, and x-axis, in y-axis it is showing clock count. We see that the number of the clock cycles required for a processor with RV32I only and RV32 with cryptography is significantly less. The size is, number of clocks are less. So now there is a performance improvement. That is what I am trying to show. So this graph is showing hardware cost versus acceleration for each of these applications. So It means that if you look at this particular present application, this application you require, there is a hardware cost of about 75%, 7.5% for an acceleration of 8 times acceleration, right? So different applications require different subset of instructions, and they have calculated it against that. So hardware cost versus acceleration is there. So in this work, in this implementation of RISC-V with cryptographic extension, they have reported execution speed up from 1.5 times to 8.6 times. We now know that if you replace, if you use these extensions, your code size reduces because complex cryptographic instructions are added. So there is, for this implementation, there is a change, there is a reduction in program size from 1.2 to 5.8 that will actually reflect as execution speed to some extent. Then hardware complexity, from 0.3% to 7.7. If for present, if you see for these set of applications, significant complexity in hardware is there when you introduce these extensions. So this is one method of implement. So like this, lot of different works are there. So if you see, Vega has a bit. Vega doesn't have cryptographic extension, but it has float, single precision, double precision, bit manipulation extensions, etc. So all these extensions add hardware complexity to it. Here, this particular, generally when you come up with a design, you have to evaluate the performance of such systems by using the target application. That means you have to execute a program without this extension and with this extension, and look at how much speed up has happened, how much clock cycle has taken for both these implementations, and that comparison is what is represented here as execution speed up. Okay, I hope this is clear. So next step, so this is, please understand that this is just one example I have shown. I had a number of different companies, different processor designs are in literature, and you may be able to look at them and use them also because it is open source. So next implementation is customization, custom instructions. That is, as I said, you don't want to use existing definition of extension. You want to use your own, because you are an expert in that area and you know exactly what is required for that particular security application, and you just want that hardware. So that's why you are working on custom design. So I am giving you one or two examples of custom designs here, and how they have made it faster is just what. So the theory behind it will is not depicted here, but how they have worked on it is what I am discussing. So in custom instruction, one method of speeding up the execution is to come up with a subset new instructions which map to frequently used functions in that particular application, right? So for security application, Galois field arithmetic is the basis. Most of the processing that happens, the operations happen there for are following Galois field arithmetic. So who actually is a group author of this paper, and there are multiple papers in this area that they have worked on. They have worked on coming up with the new instructions to support to speed up Galois field arithmetic. And then since cryptography is one application of it, automatically cryptographic applications get faster. So right hand side shows its pipeline, the pipeline. So they have worked on Swerve core, which is an open source course. If you search, GitHub has, you will find an instance of this in GitHub, and you will be able to use this. So this is based on Swerve core, and this is showing it, which is a 4-stage pipeline core. And they have introduced their own GF opcodes. So you have to come up with your own definition of opcodes. And so change the decode stage, and you have to also come up with hardware that support this opcode. So mostly addition, multiplication, inverse, square root, these functions have been incorporated. So this particular slide is showing you how the encoding is there for these four new instructions they have added. And once you do that, they have evaluated that for these applications, AES, Reed, Solomon, and Classic McKelvey, they have shown significant improvement in performance, which is at the cost of area, and correspondingly there will be a number related to power there. So that's what this is. So this is an example implementation. If you want to look at the next implementation, this is showing you post-quantum cryptographic implementation. Again, this is loosely coupled or tightly coupled? I hope by this time you know that this is part of the execution unit, so it is tightly coupled. So here again, this is another example of tightly coupled accelerator, which is for post-quantum cryptography. So it is using another open source core. Pulpino is a platform available, and the core is a post-stage 32-bit. So CV32E40P is a core available, and what this does is it has come. This particular work has 29 new instructions to speed up post-quantum PQC. And if you see, the orange color parts are the different new components that have been added in execution unit and decode unit, register files, etc., to support this. So at different stages they have, it's more complex design, but they have added, and they have shown that there is performance improvement using this. So by this time, you should understand that if you want to do something custom for a particular application, you should have the domain knowledge of that application, and then you should be able to come up with identify frequently used tasks and identify tasks that are simple enough to be included in the execution stage, and then have an encoding and then incorporate that. And then you will be able to come up with a tailor-made RISC-V design which is supporting that particular task. So that's the main idea of custom design here. Okay, so next we will look at a work that my group, research group, is working on, where we are trying to see whether both the examples that we discussed, both the techniques that we discussed previously, have instructions which are complex in nature, which have to be realized using hardware in the execution stage itself. And as I said, if clock frequency doesn't change, then you can, the size of the code change in the reduction in code size directly maps to the performance improvement. But many a times the task will be complex, as a result of which, when you introduce, if you see this diagram, introduce something in execution unit, it will have a delay which is greater than any other component. And we know that in a pipeline, a critical path or a stage which has maximum delay decides what is the clock of that pipeline, and automatically it reduces the frequency of operation of the design, and then performance reduces. So though you have a small program to run, because clock frequency reduces, acceleration will happen or not. You should actually implement, and after implement only you will exactly know. There are methods to observe it, but still, before actually tip is realized, but still there is work required there. So we try to look at options where can we realize these security applications using already existing simpler workloads, simpler extensions. So we have used bit manipulation extensions, because when I discuss, and specifically I'm looking at scalar, that is embedded applications, scalar extensions that I'm looking at, and we are targeting embedded or general purpose computing application. So we already have seen the scalar core instruction set, and we know that bit manipulation a subset of bit manipulation instruction is part of the cryptography also. So we have tried to look at whether we can use it and speed up the execution of these applications. So what is BMI? Bit manipulation IS instruction has 104 instructions with 10 sub extensions, and the table shows different sub extensions, and the ones that are tick marked are extensions which have been ratified. Others are in a draft stage, so which may change. That is what we are looking at. So when you look at them, these are instructions that could be used for address calculations or basic, that is AND or XOR kind of applications, bit manipulation applications, bit extraction, careless multiplication, then matrix multiplication, permutation, and single bit instructions. All these things are ternary bit instructions are the ones, and each subset has dedicated operation that is happening. And there, in the definition itself, subset of different instruction set has been defined. So the compiler supports these ratified instructions. So this is a snippet of the BMI, bit manipulation instruction, and here we are showing an example using CRC. Where left-hand side, it's a listing of RISC, like previously, RISC-V RV32I ISE, and on the right-hand side, I have used bit manipulation in AND N instruction and replaced some of these instructions here, and there is a reduction in one. One instruction here is only shown here, but what I want to highlight is there is a size decrease. So this is the C code that is executing is shown here, listing using RV32I and then RV32I and B. That is ZB instructions are there. So we see that there is at least one decrease in one code, one instruction in the resulting code. So that decrease in code is actually related to decrease in the code size of the program. So on the right hand side, we are showing you the code size for SHA and AES. Using GCC compiler, I said that bit manipulation support is there, using different optimizations, and the code size decrease in code size with respect to the base instruction set is shown here. That 5% decrease is there for AES on an average, and 16% decrease is there for SHA. That is for bit manipulation. If you use bit manipulation, there is a improvement in performance for this application is what I have tried to show here. So based on this this finding, first we are discussing our work where we came up with a bit manipulation instruction execution coprocessor. That is coprocessor. So this particular block is a coprocessor which has execution hardware for all bit manipulation sub extensions, and this has been integrated with it. In this case, it's a work of an MTech student of mine. This is in collaboration with IIT Madras Shakti core, and this particular extension was integrated with Shakti's E-class core. But integration is, because it is a coprocessor, we have to have a different interface where pipeline to bit manipulation hardware communication should happen. And for that particular case, they have used interface called scope interface was used here. So what happens is that when you fetch an instruction, you check at the decode stage, we check whether it is a bit manipulation extension instruction or not, or that is it related to a scope interface or not. If it is not a scope interface, it is a normal instruction, your normal pipeline execution will happen. But if it is a bit manipulation instruction, something that has to go through scope, then it will be communicated to your hardware and hardware, I think in the next, so that means it will be communicated to hardware response of, so that is a request to your coprocessor, and after coprocessor performs the action, a response will be available, and that will be intimated through the interface itself, and then you can progress with the rest of the instructions. So this is how a coprocessor implementation looks like. So, like I said, handshake signals are there between the core and the BMI execution unit. So in the second stage, you check whether it is of type, that is scope is the interface name, is the of type scope. If no, then it is a normal execution. If it is a scope interface, it has to be used. Then is your interface busy or not is what is checked. If it is busy, you will wait until your interface is busy. That means your coprocessor is busy. So you have to wait till it becomes free. It is catering to your previous request. If not, you request to send the request. So what do you mean? Typically, what do you mean by sending the request is that you will send the instruction and the operands required for execution of this instruction through the scope interface. So, which will be accepted by the bit manipulation coprocessor. Execution of that will happen, and then your response will be available. If no response is available, you are waiting for the response. Once BMI, the bit manipulation unit completes execution, it will provide a response, and if and that response will be catered to using a trap response. If it is a trap, then through trap we retire the instruction. That is how it happens. If it is not a trap, then it's a normal commit. So this is showing you a handshake of how you can include a coprocessor. It's a typical handshake that I have shown. Different implementations may have different implementation or different handshake techniques to use. So this is this is a RISC-V SoC with bit manipulation support is called VSOC. So that's the implementation we have seen. So Shakti VSOC is the name that we have used, and it was evaluated. So any new design that you do, as I said, has to be evaluated by running some standard applications. They are called benchmarks. And in this particular case, because we have used a embedded class processor and we are targeting embedded applications, we ran entire mbench suite set of programs, and these set of programs consist of different kinds of applications, which also includes cryptography. Okay, so these graphs show the geometric mean of size of the code, and blue one is standard SoC, and the orange one is SoC with bit manipulation. And in almost all the cases, we saw that the instruction count reduced, and then we looked at its speed up that has happened by counting the number of cycles that are required. These are all different optimizations that are mentioned for compiler. Overall, when you see, we see that in most of the applications, this is the summary of result for all the applications in the suite. And for SHA, core size reduction of 20% happened with a speed up of 1.42. So we saw that on all instructions have an performance improvement happening, and specifically in what is important is that there are these security related applications in mbench also. We were able to see significant performance improvement. So this is an implementation where bit manipulation unit is, that is, it's a kind of a co-processor and not tightly coupled. So next extension, then what we did, based on the previous result, we found that the results are promising. We integrated it into our execution pipeline itself. So here to do that, we started our collaboration with a startup, indigenous startup, which is working on RISC-V processor design, and we used Azurite, which is embedded class core, which is developed by the startup called Core Semiconductors. So what we did for them is that we had already designed a bit manipulation box. We optimized it and integrated it with the execution stage of the Azurite core. And then for this particular we only used ratified BMI extensions A, B, C, and S. We had seen that. So look at this diagram. It is showing you how based on the sub extension, each sub extension has different tasks. So hardware for that is different. So for each sub extension we have a different hardware to execute that instruction, and then based on the control signal, that is based on the opcode, we will be able to identify to which hardware it is going to be mapped, and then that hardware is responsible to generate the result. So this is what happens inside VBox. VBox is the name that we gave to the bit manipulation extension implemented, and we ran same mbench application to look at what happened to what happened in this design. And we see that almost in all applications, this is the improvement in cycles that has happened, and almost all implementations we were able to see performance improvement and code size reduction, which map to performance improvement. So we emulated it in FPGA, and we were able to see similar performances there also. Okay, so we have an area overhead, but that area overhead is corresponding to implement if the core already has been overhead. That is what we want to say. So in these experiments, we saw that AES is, if you see, there is a subclass of extension called ZBC, that is ZBC, which is Clarius multiplication. We looked at instruction, the disassembly of all applications, and instance of this Clarius multiplication was not coming anywhere, or the compiler was not able to identify C code which can be mapped to that. So we specifically worked on Clarius multiplication and tried to see whether we can improve the performance of these cryptographic algorithms by using these instructions, by having a good understanding of as such. So the C program, we analyzed it, and so this particular work is a combination of hardware and software designing. The AES or the cryptographic algorithm we chose, in this case, results are presented for AES, but we have worked on Reed-Solomon and McAllister also. So we look at a particular cryptographic application. I understand the flow and identify places where these Clarius multiplication could have been used. So and then generated a binary which has instance of Clarius multiplication, and then this is a simulation result. That is, we used Swerve core which has bit manipulation as ZBC, that is Clarius multiplication already, and ran this application and looked at what happened by looking at number of cycles that were executed. So we see that with if your core has already has this Clarius multiplication instruction set extension from bit manipulation, without custom instruction itself, these AES we were able to get 78% improvement. No compiler modification required. Modification that we have introduced is we have ensured that these instructions are called. So for that can be solved by having a library which ensures that these instructions are executed. So no area overhead, no compiler modification, we were able to achieve good performance improvement. So that's work. So this particular work targets cryptography only, and we were able to see an improvement in performance without hardware overhead. So now what this presents is that custom. When I talk about custom, it is we have already seen a work by Co where custom instructions were included. Now, because we are considering AES needs only 2 custom instructions, and that particular work where new instruction itself was included had an 81% performance improvement with area overhead, and this is using this is the result of FPGA emulation on RTX series of FPGAs. So, and if you want to use this, compiler has to be modified because you have to ensure that this custom instructions are included in your program. So in your actual program that is running in the execution. So this is custom, whereas proposed one without custom existing bit careless multiplication extension, we were able to get 78% performance improvement, no overhead and no compiler. It's hardware and software work together. So this is a summary of these encryption, decryption, columns using custom. That is the work that we presented, that I presented in a couple of slides before, and proposed where we are using a simple careless multiplication extension. So this is a comparison of how a work which shows that intelligently writing using intelligently writing applications to ensure it exploits the hardware provided to you. We can speed up our executions. That's a summary of it. So so these are so with this, I think what I would want to just summarize different implementations of secure RISC-V for security applications. So we have looked at cryptographic extensions. We know that cryptographic extensions will speed up cryptographic applications with the hardware overhead, which directly is associated with area and power. So generally, high performance systems would be using such. We will choose this extension implementation completely if we want a high performance system for cryptography only. And second implementation that we discussed was custom extensions or aggregators. So if it is a critical application, and then definitely you are someone who has a good domain knowledge, and so you will be able to come up with smart, intelligent ways to speed up the frequently used task or the entire task itself. So if that expertise is available to you, definitely you can try to come up with extensions or accelerators or co-processors. And when you do something like that, you will have a so definitely when you want to make something fast, you will have a complex hardware associated with it, and also to make sure that that hardware is used, you may have to change software stack. Then bit manipulation instructions, we showed you an example of already intelligently modifying the software to ensure that we use already existing simple extensions extension to realize cryptographic execute cryptographic applications and improve performance. So generally we target this, we use these kinds of techniques could be used when you are your target device is for edge or embedded application. Nowadays, as our MBench evaluation showed that cryptography has become a kind of mandatory for all normal workloads for embedded applications. So automatically, through our studies, we found that if we can speed up cryptography somehow, and when you do that, definitely there is no overhead. But you have to have a domain knowledge to ensure that C program is intelligently written. So that's that. So with that, I would want to conclude my talk. If there are any doubts that you want to ask, this is open for queries, questions. Thank you. Any questions? Okay, so since okay, since there are no, if you can let me, okay, let me know. The slides will be shared, and if you have any queries, you can let me know. Okay, so with this, I think I will conclude this session also. Thank you for your patience, and hopefully, hopefully you have gained something from what was discussed here. And tomorrow we will meet for day 4 of our FDP. Thank you all. That's all from from me today, and see you. Okay, thank you.